Welcome back to Impact Quantum, the only podcast where we explore the frontier of quantum computing and ask the real questions, like how many SAT words can we fit into a single episode? I'm your host, Frank Larvine, joined as always by the indomitable, quantum-curious Candice Gilhooly. Today's guest is Clark Alexander, a mathematician, quantum thinker, co-founder of Enerjuice. No, it's not a startup selling kombucha, and self-professed flania. If you've ever wondered how quantum computing, AI, and energy markets intersect, or how to irritate IBM with a single slide, this episode is for you. We'll dive into quantum advantage, energy efficiency, and why you can't just build a Lego tower to the moon. Expect some strong opinions, academic wanderlust, and at least 3 existential crises about your electric bill. Let's get into it.
Hello and welcome back to Impact Quantum, the podcast where we explore the emerging industry and field of quantum computing, and where you don't need to be a physicist, but it does help if you're curious. And with me, as always, is the most quantum curious person I know, Candice Gilhooly. How's it going, Candice?
It's great. I'm really excited to be here today. We
Cool.
are going, we're
No.
going, it's all good. We're going today to speak with Clark Alexander, who is a mathematician, and he is co-founder of Enerjuice. And it actually sounds really exciting, his company. So we're definitely going to be asking him some questions about that.
Yeah, so welcome to the show, Clark, and tell us all the good things you're up to with Enerjuice, which is a portmanteau of energy and juice. And in the virtual green room, we were busting out with the SAT vocabulary words. So
Right. I like portmanteau. I once got at an improv comedy show, and they're like, "Give us some words that were SAT words." And I was like,
well, we've had 2 so far. There was flaneur, which I was like, the only person I've ever heard use that word in public was Nicholas Nassim Taleb, and turns out you're familiar with his works. And then we had portmanteau immediately followed. So this is going to be the SAT vocabulary word show. So not only we learn about energy and quantum computing, but also maybe pick up a new vocabulary word or 2. But not like in the way when I'm stuck in traffic and my kids learn new vocabulary words. Those are different types of vocabulary.
Well, Frank, thank you very much for having me. This is exciting. I like to talk about what I'm working on, and I like talking about quantum computing and how it's affecting industry. And so I think we've landed the right place for today.
So. Awesome. So that's a good segue. Like where are we with industry, right? Because we had a guest recently kind of talk about how it's going to be an industry by industry type of not takeover, but it was like it's going to grow industry by industry. And he's like, will the airline CEOs care about quantum computing? Well, probably not for another 10, 15 years. But if you're in the defense or mathematics or even chemistry, you're going to care about that in a much shorter time frame. Sounds reasonable to me, but what's your take on that?
Yeah, so I want to pitch back to just 1 week ago. I was in Egypt for the first ever National Hackathon of Egypt, and it was co-sponsored by Open Quantum Institute, IBM Quantum, Quantum Africa was there, the Bibliotheca Alexandrina was there, iCafe out of Netherlands, so Taha Salim, who you may have talked to, and then Yusuf Eldakar were some of the organizers. They had invited me to, be a juror on that at that hackathon, which was amazing to see the progress being made by the university students in the wider MENA region. And then also they had me give a talk. And, my thing is I follow energy. I was an energy trader a few years ago, and, I work in AI and I work in quantum computing. And right now I'm looking at what are the energy limitations of quantum computing. So this was my talk. It ruffled a few feathers, but it got people actually really thinking about it. So sort of to put our listeners in the right mindset, those viewing, I love to start with this question. This gets us sort of in the right mindset. And the question is this: how tall a tower can you build out of Legos? I mean, like just the bricks. Just take a bunch of 2x4s. How tall can you build that tower? Okay. And if you think about this for a few minutes, well, there's kind of two obvious answers. There's the math answer, which is just keep sticking the bricks together for infinity. And then there's the physics answer, and you start asking, well, can I build this to the moon? What happens to gravity? Can I build this past geosynchronous orbit? How tall can you actually build this thing? Right.
Plus wind and like birds flying into it and stuff like that. Like,
exactly. So the analogy that we're trying to get here is that there's a math answer and there's a physics answer. And in the world we live in, this sort of mesoscopic world, here's a good SAT word for you. So in the mesoscopic world, this middle thing, the math and physics really agree really, really closely, extremely closely. But when we're talking about like galactic style stuff, right? How do you measure how far away a star is, right? You're not measuring the centimeter. You're measuring this to the nearest like astronomical unit, but you also have to consider like how gravity is bending light, right? I mean, this is a very different realm of physics. The mathematics is the same, but the physics has actually changed. Now, the same exact phenomenon happens at the quantum level, right? Quantum mechanics has its own set of rules, these physical rules that are not in this world that we live in, right? They're mostly counterintuitive. So we have things like the uncertainty principle. Right, in the big world we live in, we don't have to worry about this. And there's, I'll give you a joke, right? A friend of mine once said, I got pulled over for speeding, and the cop said, do you know how fast you were going? And my friend said, no, but I know exactly where I was. I mean, he was a physicist, and like that was a really nerdy joke, but people who have studied quantum mechanics are like, actually, that's a good point. But in this world, we can know how fast we're going and where we are kind of simultaneously.
Right.
There's some error there, but we're not concerned at 10 to the minus 35 electron volt seconds. That's not in our consciousness, right?
Right.
So, I mean, this ends up being the point, right? At quantum computing, there's this energy scale that we have to consider. There's actually a large energy scale, and there's a small energy scale. And so to start with the large energy scale, let's start with the one we kind of understand this, right? How much energy does it take to build a house? How much energy does it take to build a skyscraper? We can actually measure that pretty closely, right? So I'm looking at, say, these superconducting qubit technologies. IBM is maybe the most forward and out there. According to their blog, they use a 25 kilowatt refrigerator, which they have to run for 96 hours to get their qubits cold enough. Now, I gave this talk last week, and one of the guys from IBM, who I actually really quite like, he said, I think it's a 50 kilowatt refrigerator. It's like, okay, that's a lot of energy, right? So let's say 25, give IBM the benefit of the doubt. Their scientists have figured out some extremely awesome refrigeration technology. But
it's good to be an HVAC tech, isn't it? Sorry, I didn't mean to cut you off.
Yeah, that's right. So, but you do the math. It's 2.4 megawatt hours of electricity to get to that computation. And in this world, we can't ignore that overhead. We can't ignore that time overhead, and we can't ignore that energy overhead. And so you ask this second question: how much can you get done in 4 days using 25 kilowatt hours of electricity? That's like 400 laptops running at full tilt.
Right.
For 4 days. Like, can you get a pretty good approximation of literally anything running that fast? It's like, not everything, but an extremely large set of problems you can get a good approximation for. Right. And so I was in a business meeting a few months ago with the former head of Renaissance Technologies, and I pitched this question to him. Right. I can find you an approximate portfolio of stocks that you want to trade, which will give you, let's say, 28.1% return. Or I could run for 4 days and I could get you 28.100000007% return. And he's like, well, I'd take the first one all day. Right? By the time the stock market's already changed in that 4 days. So that 0.00007% return it's actually negative, right? Because you're paying for that in time and volatility. Right. So what this does, this puts us in the realm of what quantum computers can and cannot do and where they actually are going to be advantageous. All right. So for me, I like to sort of say exactly what is advantage and what is supremacy in the world of quantum computing. I think these words get used a lot without like really defining them. So I'm going to dig deep into my mathematical self, and I'm going to give you the definitions, and your listeners and viewers can disagree with me all they want, and that's totally fine. But from my perspective, there's three things that we measure in modern computing, right? There's speed, there's memory, and the kids who have studied like the beginning computer science algorithms will realize you can trade off speed and memory, right? You can sort a list really, really, really fast if you can memorize all of it, right? So there's a trade-off there, okay? But the third one now is really energy, right? You look at the large language models reopening nuclear facilities, data centers, how much water there, like Tulsa, Oklahoma had to go on water restriction a couple of days last year to like cool these data centers down. So this is no longer this sort of thing we think about. At an industrial scale, this is the main metric. Right. There's energy, then there's speed, then there's memory, right? Or energy and then time and then storage, if you want to think of it this way. For me, energy is like the prime metric. Now, in quantum computing space, I think advantage means that some quantum computer chip system has outperformed a supercomputer in at least one of these three things, even on a specialized task, okay? And supremacy would mean that a quantum computer is outperforming a large set of problems in all three of these tasks, okay? So advantage we've probably seen. Willow probably did this. Marco Pistoia, when he was at JP Morgan, before he joined IonQ, they did this certified randomness. I think that's advantage. I think that is advantage. They have built a very specific chip to outperform in speed, building randomness on a classical computer. I'll give them this, right? I think that actually happened. For supremacy, I think because we have at the moment we have this huge time and energy overhead, I don't think we're actually going to be able to get ahead on time-based problems. Right? So I've worked in supply chain optimization, and I don't have 4 days to cool down a computer so I can make a decision. I have to make the decision 12 hours from now. Right? If we have this overhead, that can't be discounted, and so there's no way a quantum computer can actually beat that in time, because they have this overhead that you can't get around. Right? There are physical rules to it. It's not like, oh yeah, I have a quantum computer that's just always on. Right, with that amount of
energy. If when you throw energy into the mix, then yeah, that becomes an issue, right? And I was thinking like, well, what if you rotated it, right? Like you have one on, one cooling, and I was like, well, you're still spending. You're still absorbing. Not absorbing. Yeah, you're still running a lot of energy. Yeah,
that's right. You know, and a few years ago, I was talking. I interviewed at Oak Ridge National Lab for their quantum machine learning group, and they were installing Frontier at that time, which was at that time the world's fastest and largest supercomputer. It's now moved to second. But when it came online, was the most energy efficient per computation that had ever been built. And the guy directing the building of this computer said, you know why we didn't build it twice as big? It's because we couldn't afford the electricity bill. I'm thinking, well, you guys work for the DOE, right?
Right, seriously, if anyone could, sign off on new nuclear reactors and whatnot, like it'd be them.
I mean, yeah. This is them telling me they couldn't afford the electricity bill. So there's some, like, this metric has like catapulted into like, this is the thing we actually really need to care about, right, at an industrial scale. And he worked out the math for me. Roughly, as you square the number of operations, you cube the amount of electricity necessary.
Okay, right? So this is a serious problem. It's funny because now you pointed something out that, so I live between Data Center Alley in Northern Virginia, which is Loudoun County, Virginia, which is near Dulles Airport. So if you ever fly into Dulles Airport, all those buildings are probably data centers. And 3 Mile Island, right? So one of the big controversies here is they want to plow through a lot of farmland and like put in a new power line that goes basically straight from the Pennsylvania grid to Virginia. And there's a lot of political drama, NIMBY type stuff going on. NIMBY meaning not in my backyard. It's not another SAT word really, but but I mean, like it's serious. Like it's serious. It's just like basically the way there's a lot of shady deals going on where Maryland customers are going to have to pay a surcharge for this reliability project, which is the electricity is basically going to go straight over our heads into the next state. So I mean, this is a very real problem, right? And you can look online about kind of stories about communities that have had data centers put in, and it wasn't exactly the wonderful thing that they were told it was going to be, right? So like it's interesting to see that now this is an issue, right? I long sometimes for the days when nobody cared about computers but other computer nerds.
Yeah. I mean, I'm in some ways I make computing great again, right? This
Right.
MCGA. That's what we want to do.
Make it obscure again.
Yeah, make it obscure again. I like that. MCOA. Yeah, we got the acronyms going today too. So, anyway, this is where I am about how quantum computing is going. I don't think supremacy is in the cards because there's a large set of problems that we can't either outperform on memory or time, right? Energy or time. Memory is not even in the discussion yet.
Right.
Quantum storage is not even in the discussion. I know there's a patent on QRAM, and I talked to Mohammed Zadine, who has that patent. I talked to him last week, and even he's not really a believer in quantum memory overperforming classical memory ever. And he has the patent, right? So it's not like
it's not some rando on YouTube.
Right. This is the patent holder. I saw the patent itself actually, which was pretty cool. So, any case, he's not necessarily a believer in this this third one, the memory piece. So, I think going way back to the earlier point, what we're going to have is quantum hardware built for specialized problem sets in which they can perform an advantage, and maybe two of the metrics they'll probably be able to overperform. I see this happening, right? And to give yet another analogy, I was speaking with the IEEE subgroup yesterday. We were working on our final paper for quantum cybersecurity, and I told them that we're discussing Google's Willow chip. Mm-hmm. I'm a big Formula One fan. I've been a big Formula One fan for a long time, since '92 actually. Nigel Mansell, but you can look that one. Nigel Mansell, my man. Weird dude, but good driver. In modern Formula One, they take the cars apart after every race and they rebuild them, and they sort of rebuild them to be advantageous to the track they're about to race on. Right? So this is some like really specialized race car at each track. It looks roughly the same, but they can tilt the front wheel a little bit, and they can balance the tires a little bit. So if they're going to be turning right a lot more than turning left, if there's banked turns, right? If there's a very long straightaway, they'll let the back wing come down, a tenth of a degree more. It's built specifically for the track, right? They're not allowed to memorize the track. That caused the disqualification a couple years ago with Renault. They had memorized the tracking in the brakes, like they had programmed the brakes to memorize. That caused a disqualification, but they build the car to the specifics of the track for the week. That's legal, right? to within rules. That's the kind of thing I think we're going to see in quantum computing. People are going to be building specialized systems to solve specialized problems and kick ass at doing this.
Right.
Now, where we're actually going to see some advantage, again, I was sort of jostling back and forth with IBM about this. I can solve something that will take 3 million years in 5 minutes. Okay. If that thing is worth 3 million years of advantage, then I'll give you 4 days. I'll give you 8 days to cool your computer down. It doesn't matter. Right. But stock trading doesn't fall on this thing.
No.
But if you're talking about improving, we end up speaking about the Haber-Bosch process for making ammonium, right? If you're improving that by a fraction of a percent, the payback is so enormous over just a year that energy usage is going to be wiped out, right? If you're doing something that's like a long-term massive energy reduction problem and you can solve this faster, that's advantage. That's really a thing that has happened. But stock trading, supply chain optimization, it just can't, right? You can't. There are like physical barriers which you can't do that, right? So it really has to be, for now, forget NISC. This is like specialized quantum hardware to solve specialized problems, and I think, and I'm okay with that. I think that's a really interesting scientific and engineering problem to go into, like solving. I want to solve this thing better than it has ever been solved in history, right? It's a worthwhile, at least scientific endeavor.
Well, so I'm the curious one, so I get to ask questions that sometimes seem silly. But when you're saying the quantum hardware that's able to do this kind of precision, um, why would that not be different kinds of software? Like, I'm trying to understand the difference as to what would allow you to do this kind of computation. And I thought that was more of a software thing than a hardware thing.
Um, well, at this level, at present, they're not really separated, right? Because I think I think where we are in the world of quantum computing is we haven't even decided what a qubit really is.
Okay.
There are 9 known types of qubit
Right.
technologies, and what I'm hearing, this is from the IEEE discussions. They're saying, well, each one has its own advantages and disadvantages. I mean, so have we decided what a qubit is? Well, IBM has decided what they think a qubit is, but IonQ has decided something else.
Right, because there can be used for different sectors to solve different types of problems. Like you have the ion capture, and then you have the super. When we started learning about qubits and learned that there were 9 different kinds, and every time we feel like we've got our handle on the information, there's just a little bit more that's released that we're like, no, we don't know anything.
Right, and there's two, like mathematically, there's 2 types, right? Annealing has these wires, right? So if we're going to talk about topology a little bit, the annealing is just like it's a one-dimensional qubit. It's just spin, positive or negative spin, and the neutral atom or the trapped ion or the superconducting qubits, they're like full electron spin. So the annealing one, D wave, is like an S1, the circle, and then on the gate side you have like S3, so a sphere sitting in 4 dimensions, right? This is an S3, right? So even that technology is like mathematically they're super far apart. Even how you program them is different, right? So it's just like the analogy of a punch card computer to modern digital computer. Just even that technology is different, so they're going to do different things. Although punch cards are not so useful at this time.
No, I know what you mean. You mean like what's the type of architecture we have now? Not von Neumann, but I know what you mean. Like the typical. It'll come to me later. But speaking of SAT,
Yeah,
computer science AP terms, but yeah, I know what you mean. Like a traditional, what you would call a conventional or classical computer, that type of thing. Punch card computer is a little harsh, but I know where you're going with that.
the distinction between these 2 types of quantum computers are not. It's not that far apart, but I just want to make the analogy so that the listener understands that annealing and gate computing are really separate technologies, and they require a separate set of mathematics and a separate set of programming, right? A digital computer is like, or to be reductive, it's a little bit of light switches. It's just a whole bunch of light switches, zeros and ones, on and off. A quantum computer has a fundamentally different set of physics, and so it needs a fundamentally different set of rules to program.
Okay.
Well, annealing and gate computers are also fundamentally different. Like topologically, they are distinguishable types of things.
So it's not just a new species; it's like a new category of species, right? Like
right. You just program a gate computer to do an annealing task. They're not the same problem.
So is that why companies like D-Wave, they're heavy on the annealing side of things, and they're more commercially around longer, and maybe that's an easier problem to solve?
Well, annealing's been around for several thousand years, right? And so I think it itself in, I guess, 99 when D-Wave started to say, like, yeah, actually we could probably do this quantum annealing thing and make a specialized thing, right? D-Wave has a specialized solver. It's kind of a one-trick pony, and I don't say that in a dismissive way. Like, it's an amazing trick that it does, but it does a thing. It's not going to be doing. You're not going to have a D-Wave GPT.
Right.
Right. That's the
Yeah.
kind of thing it's going to solve. You're going to have these really hard optimization problems, which you can pitch as binary optimization problems.
So special purpose computing.
Yeah. Yeah.
Interesting.
And it can solve a lot of really, really hard problems, or solve or approximate very closely a lot of hard problems, but it's in a specialized realm. It's not just a general computer.
Right.
So
That's fair.
where do you think the first breakthrough is going to happen? True breakthrough, like, is it going to be in precision? Is it going to be in pharma, with precision medicine? Is it going to be in energy with EV batteries? Is it going to be in finance for, what was that? The random number generator? Like, what do you think will be the first true breakthrough?
I don't want to maybe guess, because what's prediction is hard, especially about the future. go more quotes. But I'll say this. What I see, part of my talk is I talked about how cybersecurity is safe from quantum computers forever and ever and ever and ever. It just is. RSA 1024 is safe from quantum computers because of this. There's an energy limit on the bottom. We can talk about that later if we want, but they're only safe from this particular style of attack, right? This quantum Fourier transform Shor's algorithm is going to top out because you have to do this. You have to rotate these electrons so little, right?
Mhm.
So the readout becomes random. It's just noise, right? You can't say, I'm going to rotate this 10 to the minus 7,050, right? That's zero. That's zero rotation. The readout will just be random. Okay. There's no way you can produce so little energy to actually make that rotation physically meaningful, right? Mathematically, it's fine. Rotate as little as you want. It'll work. We proved Shor's algorithm works mathematically in the 90s. Physically, it can't, right? There's a uncertainty limit there. But what all that does is that tells us that the path that we're going is going to have some sort of limitation. When you're trying to get some sort of specificity, right? You're going to run into a limit the way we're doing it now. This does not, however, preclude some totally other algorithm and totally other way of doing things from coming up, right? Going back to Nassim Taleb, we'll go to the Black Swan, right? Earlier this year, Ken Ono, who's an amazing mathematician, he's a number theorist, actually, I think was working with Katie Ledecky, the swimmer. They were doing some,
Oh,
so he helped her with
that's
like
cool.
tracking the statistics. But anyway, he's a number theorist, and he and two of his students, Craig and I think von Itterson, they put a paper this year redefining what prime numbers are. And they said, actually, we found out that if you take this polynomial and this partition function, partition is just the number of ways you can add up a number to get there. So 5 can be added up as 4 and 1. It could be added as 3 and 1 and 1, or 3 and 2, or 2 and 2 and 1, right? These are partitions of 5. How many partitions of the integers there are? This polynomial times this partition function plus another polynomial times another partition function. It works only on primes. It's just this sort of like magical thing. We've been thinking about primes the same way since Aristophanes, right? 2,600 years ago, right? We've been thinking about primes this way for a long time. And now just this year, 2025, we say, actually, there are infinitely many more definitions of primes. This is the black swan, right? And so, let's go. I love this this quote. It's from The Zero Effect, 1998. Bill Pullman's character says this thing, and even though it's a comedy movie, it's so like philosophically deep. I kept it. It says, if you're looking for something specific, your chances of finding it are very bad because of all the things in the world. But if you're looking for anything at all, your chances of finding it are very good because of all the things in the world. And I think like this is where we are in quantum computing right now, for specifically for internet security, right? Somehow there's a magical way in which most technologies have two different sets of competing technologies, but internet security has never been that. It's just been key exchanges. Okay. And so factoring large numbers has basically been what internet security is. Well, now you just need one algorithm to break any one of infinitely many definitions. I'm looking for any one at all in any way, shape, or form. I'm not precluding this possibility at all. In fact, the chances of this not happening are 1 in infinity, right? It's going to happen.
Right.
This thing is going to happen. By whom? I don't know. Where? I don't know. By what type of algorithm? I don't know. But the fact that there are so many possibilities now, it opens it up in a way that we haven't been thinking about, right? And this is brand new. This is 4 months ago that this paper came out, right? So we're not there yet. So internet security, maybe at least the integer factorization part. What I see actually happening, and maybe I'll ruffle some feathers here. A good friend of mine I went to undergrad with is now at Flatiron Institute. And if you follow Flatiron Institute, these are 4 guys who they take all these claims about, oh, quantum breakthrough happens. Chinese researchers have done XY thing that a supercomputer could never do. And about 6 months later, they say, actually, we did it on a laptop. They've done this like 4 or 5 times. Flatiron Institute, they do awesome stuff. And for me, talking about quantum impact being on this like particular podcast is important, that the real measurable economic impact of quantum computing is it is causing these guys like Flatiron Institute and guys like me who work in evolutionary programming to rethink what our classical algorithms are doing. We are getting better and faster and smarter classical algorithms, which are costing less energy and less memory to do better things to sort of push quantum advantage back. This is a
quantum-inspired algorithms. Generally the okay.
Some of them are, and some of them are just like, oh, you know what? There's this randomization scheme we just weren't looking at.
Right.
Some of them are just pure randomized algorithms with like a really clever way to do stuff. Right now, I give this example. Like, someone showed me this is the slickest line of code I've ever seen, and it was for a video game where when you're looking around in a video game, what they want to do is make all the vectors are normal. So like when you're looking at the spot, you turn around and you look, and what this looks like mathematically is you have to take this ray of vision and you normalize it to length 1. All right, so going way back to vector analysis, you take the vector, you divide it by its length, right? So square root of it. And so this guy found this way to just take an inverse square root really, really, really fast. And the way he did this is basically he got a really good first guess and 1 linear approximation. And that's absolutely brilliant. That's what he did. He took a really, really, really good first guess. And so this thing can sort of run, and it causes much less lag. And you can see this happen in like, area games. So he's reduced the lag across the entire network of all video gamers worldwide by just this clever, right? That's pure classical algorithm, but it was like a really awesome randomized first guess. He figured out how to do that. Right? No quantum, nothing. It was just like, oh, if you start near the solution, you only have to do a little bit of computation to get to the real solution. So some of it is quantum-inspired algorithms, absolutely 100%. I work in that sort of area. Genetic algorithms, Monte Carlo simulations. I think there's this like biased field, diagonal cross optimized something. It's a terrible acronym that has no word to it. But this to me is like just the quantumized version of this 1992 algorithm called MC. There's 3 MCs, which for the listeners will be Metropolis coupled Markov chain Monte Carlo algorithms. In case you're wondering.
So it's not a rap group from the early 90s then?
It unfortunately is not. No, it's not in the native tongue culture, right? I know Queen Latifah and De La Soul would have put out the album of the 3 MCs, but
that'd be awesome.
Unfortunately they did not, and it got into like philology in biological classifications. But I use this actually for supply chain optimization, because the point is that instead of just guessing this one spot like Monte Carlo algorithms do, it allows you to guess many different Monte Carlo algorithms, and so it allows you to find multimodal probability distributions a lot faster. It converges so much faster. Right? It's just pure probability, and I think that actually inspired the quantum algorithm for the biased field diagonalization. At least to my reading, that's how it looks. Right? So the quantum algorithm is classically inspired, not the other way around this time.
Gotcha.
It goes both ways, right? This is
interesting. You wouldn't have thought of that kind of naturally. You would not have thought that the classical inspired algorithms would.
I don't know if the authors of that algorithm were thinking of it that way, but you know, having used the classical algorithm myself multiple times, and having read their paper, at least to me, it was just like, you know, my neurons were lighting up. My neural network was saying, "Oh, these are the same algorithm. These are the same algorithm."
Mm-hmm.
That's how it rang to me. They might not have been thinking about that, and that's cool that they have like a totally unique algorithm. But you know, I've seen this algorithm before as a classical thing.
Interesting.
So even if they didn't know about it, you know, this same sort of technique landed, right? It's like the name Soren. Soren is a Persian name, but it's also a Swedish name. They just sort of landed on the same letters.
Right. Interesting.
That's my take. Could be wrong, but that's how I read it.
I'd love to just take a little step back if I could. I mean, what you do sounds legitimately fascinating, and you know what you're uncovering, and you're at the frontier of innovation. You know, I'm going to ask you, like, walk me through a little bit of your career journey that got you to where you are right now.
Okay. I hope you guys like random walks because.
That's the only type of walking I do.
Fantastic. Okay, you'll appreciate this. I've done a couple of I've been to support this program in Mexico a few times called Qubits de Ciencia, and one of my former students from Northwestern is one of the founders of this. So he invited me, said, "Come talk." And one of my favorite events at this week, it's like a 1 week intensive where instructors from Mexico and United States come and teach like a 1 week intense course on some sort of science to high school seniors, college freshmen, college sophomores in Mexico, right? Because there's a lot of talent coming and they just don't have the resource. That was the point. But Wednesday night of this week, whenever they do it, they have like the science cafe, and they have the instructors, me and some professors from University of Chicago, from Harvard. They come and they ask us questions. And someone asked me about how do I think about work-life balance, something like this. And I said, whatever you're expecting in the future is wrong. That's it. But
let's just start there.
Yeah, but what that means is that some things are going to far exceed your expectations, and some of your expectations will never even get close.
Right.
Okay.
Right. So that's kind of, and that's kind of how my life has worked. So I'll give you like just the really top-down overview. I finished my PhD in 2008 in non-commutative geometry and mathematical physics. What I have learned reading a lot the last 2 years is that historiography is a chaotic system. If you start the story 1 year earlier, it changes the whole story. So in 2007, there was a whole hiring spree for non-commutative geometers in mathematical physics. And this was spurred on by Alain Cohn's idea that he may have solved Riemann hypothesis using these mathematical physics techniques. There's like this glut of non-commutative geometers getting in postdoc positions. So 2008 comes around and I didn't get one of those postdoc positions. I got a teaching job at Temple University. Go Owls. It was awesome. But
I was going to say, at least you didn't work for a mortgage company. So
right. Well, almost happened. You know, thank Baal it didn't, right? Go randomness all the way. 2008, you may have remembered there was like a massive financial crisis. So there were a lot of postdocs of 3 postdocs for 3 years got shortened to 2 postdocs of 2 years. So I got double caught up in that. And then I basically became what they would call in the sports world a journeyman. I went to Southeast India to Institute of Mathematical Sciences for a year. And then I came back. A professor had died days before semester was supposed to start. And I just ended up getting a job at the University of Wisconsin Parkside to fill that. That was completely random, only because I had known someone here in Evanston who was doing this. I taught there for 2 years. Then I landed at DePaul lecturing 1 year. I was at DePaul for 6 years, and then I moved to UIC for a half a semester. And I never was going to make tenure, right? Those days had kind of passed for me in some sense. And so a friend of mine who I'd gone to Northwestern with had started a company, and he called me and said, Clark, I'm doing this thing in data science, but it's not traditional data science. I need some real mathematical firepower, and I don't have it. You want to come work with me? And he went to my wife and said, you need to convince Clark to come work with me. And so my wife said, Clark, you need to go work with him. My friend Rami pulled me out of academia and started me into industrial mathematics. And I didn't know how to program a computer, and so I learned there. Rami unfortunately got sick, and he died a few years ago, and so I kind of have made my way from there. He got sick, and then COVID happened, and I left that company, and I joined an electricity trading company through another roundabout connection that I knew from India. Completely random. A mathematician was like, I want a mathematician to help me trade electricity. Okay, so I did that. There was an electrical storm in Texas, you may remember, like there was an ice storm. Everyone lost all their money, so my company went under. I lost a job again. Fantastic. Started just applying everywhere. That was when I was applying at Oak Ridge, and then I ultimately took a job at a credit card company. That didn't work out for whatever reasons, and then I joined a logistics company where, aforementioned, my friend Rami was supposed to be the head of AI, and when he was really sick, he had called the CEO and said, hey, you need to take Clark. And so that's how I landed there.
Interesting. You mentioned a couple of times energy trading. What's the dollar store description of what energy trading is? I'm not quite sure, because I know it comes up a lot. Usually when there's a crisis, people are suddenly experts on energy trading. But like the Texas crisis, plus there was some drama in the early 2000s in California. And I think the most infamous energy trading company in the world is still Enron.
Indeed. Many orders of magnitude.
So, yeah. Well, if you're going to blow up something, blow it up big. But what is energy trading? I don't quite get it, right? Because and this has come up, I'll tie it back to the issue with Maryland and Virginia and Pennsylvania, right? Like they're talking about they buy energy from here, and they do that. Like I don't quite understand. I can understand how the math would work in terms of optimization and probably what you do, but I don't understand the industry. And I realize this is the quantum podcast, not energy trading. But what's like a good $2 description of?
Okay, fantastic. I'll give you two really easy problems, and then I'll tell you why quantum computing is important. Okay. So
good, you're tying it back in.
That actually just happened recently. It'll tie all back in. Great. So there's two ways the energy trading sort of works, right? The easiest one is you go to a city, let's say Madison, Wisconsin.
Right.
Wisconsin goes to the regional transmission operator or independent system operator, depends on how they're named. So you've heard maybe of CAISO, that's California ISO, and then you've maybe heard of MISO, which is where I am, Mid-Continent Independent System Operator. So the ISO or the RTO controls like all the energy flow, and it controls the pricing. So the city of Madison, Wisconsin will say, okay, I want to buy, is basically a futures contract. I want to buy this many gigawatt hours of electricity that you give me from January 1 to December 31 of this year, and I want to pay this much per kilowatt hour for it ahead of time. And in this way, Madison, Wisconsin can now sell to their residents at whatever marginally marked up price, right? So we want to buy it for 12 cents a kilowatt hour for the entirety of the year, and we're going to make a deal for, let's say, 500 gigawatt hours, whatever they make. I don't know how much Madison uses, and then so they sell it to all the independent households and the schools and the businesses for 15 cents a kilowatt hour, and that's just the price of electricity for the whole year. All right, that's one way to do it. That's a forward futures contract. Okay, they make the deal. The one in trading, so you could do that if you're a municipality, you trade this way. If you're an individual little brokerage house, you will say, okay, the ISOs and the RTOs actually set the price of electricity. And what they do is they say, okay, 9 a.m. today, so this is just a few hours ago, they set the price for tomorrow's electricity pricing. They set it at 5 or 15-minute increments, depending on where you are. So say every 15 minutes, we're going to charge this much for electricity. Okay. This is called the day ahead price. Okay. And so what happens is these little traders can come in and say, okay, actually, I think it's going to be less than that. Okay. The real-time price is going to be less than that. So what I'm going to do is buy the real-time price now and sell it at the actual. I'm going to buy the day ahead price and sell it at the real-time price, right? So they make some money. Or you can sell it as like short selling. Basically, you can sell it. You think it's going to be too expensive. You sell it and then you buy it back at the real-time price. Literally trading. This is called day ahead real time. So in trading, they call that the DART model, DART, right? That's the simplified version. And then there are options, all sorts of exotic options and hedging and all kinds of stuff. You know, they run it like a hedge fund, except that the commodity they're trading is time-based. Very, very, very strictly time-based. That's how it works.
Okay. So, you know, Con Ed is kind of like the supermarket. And then whatever the supermarket buys their food and their groceries and distributors is kind of like that, the back office to all of that.
Right. And so the RTOs and ISOs have this question, like, how do you set the price? And so what you want to do so this is a massive, massive optimization problem. This is probably the most important, most worthwhile optimization problem you've never heard of, called the ACOPF, this alternating current optimal power flow. So what you want to do, if you're making the electricity, if you're a generating plant, you don't want to distribute more than you've made, and you don't want to have shortages. So you want to balance the best you can in real time the supply and demand of electricity. Okay, this takes into account congestion, where there's construction, there are voltage angles, there's like there's all sorts of things pricing. So if you're a mathematician, this is the most exciting problem because it's non-convex, non-linear, time-dependent, directed graph, acyclic graph, cyclic, whatever non-thing you can think of. This is the problem for you. And like a 0.1% in improvement. I think I did the math on this. If you improved the efficiency of this solution by 1% and are actually able to successfully trade on it, it's like $1 billion a day benefit.
Oh wow! So no wonder why it's run like a hedge fund.
Yes, but like bigger than that, way that, right? Because the electricity market is so much bigger than the stock market, because everyone uses electricity all day, every day. Right, and it trades on companies and trades on everything, and there are options, and there are municipalities, there are big players, there are little players. This is a big market. We're talking like size of 4x. I mean, massive market. So
wow,
the ACOPF, extremely difficult. The way that people make money is that the optimization is called the DCOPF, and DCOPF is direct current optimal power flow, and that has a convex solution. So you can simulate this and solve it very quickly on a digital computer. You need a supercomputer, but you can solve it quickly, right? Minutes, right? It's a minute solution, not a millions of years solution. So one of the main problems, the ACOPF has sort of sub-branches. One is about pricing and one is about actual energy delivery. It looks like IonQ has recently worked on the unit delivery problem. So given a particular power plant, where does it deliver its units of energy? I guess they're doing them, they're probably scaling them in kilowatt hours. Where does it deliver kilowatt hours at 15-minute intervals? That is an extremely difficult problem, and it looks like IonQ has tried to tackle this, at least at a small scale.
Right.
So this might be one of the major breakthroughs. Just the problem is the amount of memory needed. I think it will overwhelm any quantum computer that currently exists. But this might be one of the major things. But ACOPF is like worth not a little bit of money. It's worth a lot of money, extreme amounts of money. So
wow, this has been interesting, and I like the fact that this is literally every time you flip the switch, like this is a mathematical problem. So kids, if kids are listening, math is super important. And
that cannot be said enough.
Seriously.
Yeah. But look at the exciting things he's doing, because he started with math. I mean, this is just outstanding, interesting. Like this would captivate any, any Gen Z kid out there. Be like, you
That's
know
how you
what?
can tell she's Canadian. She lives in Canada. She's not
Right, because
born
I say
Canadian.
Zed.
Yeah.
Born New York, born New Yorker, born and bred. But now I say Zed because I'm in Canada.
Still on mid-continent ISO.
Honestly, Clark, you've been absolutely fascinating. I've loved every second of this, and I absolutely want to have you back on because
For
I have
sure.
so many more questions to ask that we didn't get to. Um, so I'm blown away right now. I've learned a lot. I've learned a lot, and I have to like digest,
Just
to
the explanation of the electricity markets and how they function is worth it. Because all I remember is, oh my God, Enron did all this fraud. And then you didn't hear about it for years until everything went sideways in Texas. And it's like, oh well, the energy companies blame the energy traders, blah 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 blah. These people do this, and I'm like, oh, these people again.
Yeah. So that was a totally different issue. Maybe we can get into that if we go again.
Yeah,
next
another time. Yeah. But where can folks find out more about you and what you're up
time.
to?
Basically, I'm mostly on LinkedIn these days. I'm starting another venture called Argentum AI, which we're trying to do energy efficiency um, in AI training, right, and locally distributed training. So Argentum AI is one of my things. Enerjuice, we're trying to do some projects with the DOE, but mostly LinkedIn. I'm kind of just mostly there most of the time. Um, yeah, and if you're into soccer, I'm the local soccer commissioner in Evanston. So come out and see me on Sunday.
Cool.
That's awesome. That's awesome.
And we'll let our AI finish the show.
And that's a wrap on another episode of Impact Quantum, where the topics are dense, the qubits are entangled, and the guests are occasionally flaneurs. Huge thanks to Clark Alexander for joining us today and proving that mathematics isn't just useful, it's a passport to energy markets, quantum hardware, and mildly unsettling jokes about the uncertainty principle. If you enjoyed this episode, be sure to like, subscribe, or entangle yourself with our past interviews. You can find Clark on LinkedIn, Enerjuice on the cutting edge of renewable innovation, and Candice trying to remember which qubit type is currently trendy. Until next time, remember, classical computing may be fast, but quantum computing has better party tricks.